Yes, good evening, everyone, and welcome to today's webinar. So yesterday we had the first presenter was Brian Macharia. So he presented alone, and then we had Brian Gillo. The partner was, I think, Obsagay. Then we had Eugene Gusmao. He was solo. Then I had Warren Munene and his team, Hilary and Amani. Then I had Kirui Brian. His team members were Uvria Brian and Abraham. And then we had Kennedy. Yeah, so yesterday we had 5 teams. Yeah, so today we expect more presentations. Yeah, so thank you. Can proceed. Anyone who is ready can proceed and present their. Okay, yeah.
Good evening. Hello.
Yeah, hello, we can hear you.
So can I talk?
Yeah, go ahead. You can start presenting.
Okay. So good evening, everyone. My name is Brian Macharia, and my project name is Aries EV, and I was working on the urban mobility problem. So my design phase had two phases. Had the drivetrain simulation. So this was to determine the optimum parameters that I would need for motors, the battery, and for such. So, and then the second part is the car design, which is done in Blender. So for the MATLAB simulation, I had several things that I was working with. So, first of all, for my design parameters, I wanted a range of 250 kilometers, and then a battery voltage of 300 volts. Then the rest of these, also a gear ratio of 6, and then the rest of these were determined either from estimations such as the vehicle mass or from actual simulated results, so such as the frontal area in this case. Then for the modeling, I used Simulink, and in this case, I only have just 4 models. So there is the vehicle model, is the transmission, is the motor, and then there's the battery. So what this is supposed to do is actually just give me the motor torque, speed, and power, and then the battery parameters that I will need for the development of the drivetrain in this case. So I'm simulating this with FTP 75 drive cycle. This is a common drive cycle used in the US, and it simulates an urban driving environment. This is why I choose it in this case. So for some results that I have, let me show you some scopes. So these were some of the results that I got. This is for the speeds and torques. So the motor torque and the motor speed. As you can see, for the FTP 75 drive cycle, I had a maximum torque requirement of about 150 newton meters, with the motor speed maxing up at about 5,300 RPM. And then for the batteries, then the motor power is about the required motor power is about 50,000 watts. The battery current of about 180 amps in this case, and a battery C rate. So the charging and discharging rate of In this case, this was about around 1.75. Again, this is using regenerative braking. So as you can see, there's some parts that are going upwards. This is a state of charge graph, and as you can see, there is parts of it where it moves upwards. So actually, the graph at the bottom here is a velocity profile. So as you can see, at points where it's slowing down, then the vehicle is actually the state of charge increases to show that it's actually charging in that case. And this sort of improves upon the efficiency of the vehicle. So this is about the modeling. Then I can go on to the actual car design. And this is, so I used a combination of two softwares. In this case, I used SolidWorks and I used also Blender. But mostly, majority of the work being done with Blender in this case. This is a general design of the car. It's a 7-seater with uh, 6 seats for the passengers, and then it's a small vehicle, just the size of a normal Noah, or yeah, the size of a normal Noah in that case. Then, so just to show you some general things, the outside of the chassis, the vehicle body, is what it looks like. Then there is the seats. So this is the seating arrangement, and also there is the yeah. So this is the seating arrangement of the car. Actually, you can put in the other car. And this is sort of the interior of the car. There's, as I said, there's 7 seats. There's a lot of space. So 2 in the front, 2 at the middle, and then 3 at the back. Then for the drivetrain, this is the drivetrain. It has, so the car is actually rear wheel driven with a single motor, and then this sort of drive unit will contain the motor and also the inverter in this case, and also the DC to DC converter. Then there's a suspension system um, at the back, and then a double wishbone suspension system at the front in this case. And then for uh, the battery has 4 layers. So first of all, the casing is designed to ensure that the battery is safe from heat. And in this case, we have the battery holder having sort of heat sink at the bottom. So air flows from the front and passes through the sinks in this case, cooling, providing additional cooling to the batteries. Then if I sort of remove things in the battery, there is a top layer. So this is a foam material that sort of dampens vibrations, so providing additional protection to the battery. And then underneath that is the batteries. So there's 100 of them, in this case, all connected in series. The battery type I'm using is lithium. That's lithium-ion polymer batteries, and I use them because, first of all, they're cheap, and then we have high capacities. So you can get one of these batteries at 3.2 volts, but having a capacity of say 150 amp hours in this case. Then there is a cooling pipes um, in the middle of the batteries. This provides additional, so there is a pump at this point that circulates coolant that will also aid in the general cooling of the battery to avoid thermal runouts. And so, yeah, so this is the cooling of how it is. So this is the bottom, it's on the bottom and also on the sides for maximum heat dissipation. And then, yes, so that's actually about all my design. Uh, Part I can show you the again the overall design of the body, and in this case, uh, this is what it looks like from the back, from the sides, and then the rendered view. I was going for a simple design that's sort of futuristic but also combines uh, that olden style of design. And you can see it's sort of mimics the front sort of mimics an old Volkswagen counterpart in this case. And then this is the render with the colors as I imagined them to be. Yes, thank you. Sorry? Okay.
Hello, from Team Safari. Hope you can hear me, guys.
Yes, we can hear you.
Okay. So I'm from Team Safari. I'm presenting. We are a team consisting of 2 members, I and my team member, Jim. So we're presenting the Loft electrical vehicle. The Loft electrical vehicle is a sun-powered sanctuary on wheels. We have reimagined the traditional car. So what we identified that there's a very huge urban noise pollution, air pollution, and traffic congestion in most urban cities. And thus we came with a Loft electrical vehicle, a semi-autonomous vehicle, transforming the way we think about mobility. So the inner space is maximized to create a lounge-like atmosphere, giving it a stylish kind of a vibe. So on the outside, the Loft AV is a minimal aesthetic with a sleek glass frames that floods the interior with natural light, creating a very perfect, inviting vibe. So that's our mood board. That's our sketch. So as you can see, so we have designed it more. It's a six seat layer. The two front part are rotating, and this other part are more of like a sofa set, kind of a lounge style sofa set, giving you a chill ride where you can have a conversation in the cabin. So that's our cabin interior design. So this is a side part. So the best thing also, it has a sleek LED stripe lighting integrating into the body of the cab. Stylish, practical, and seamlessly rhythm in the urban life. So we are creating the future of electrical vehicle. We identify that, yeah, electrical vehicle are there, but what are the most unique aspect that you can blend in? So the best thing, we are driving sustainability in the Loft EV, being powered by a cutting-edge solar technology, integrating in the rooftop. So this, which will, it's the solar panel will act like an additional power source. So looking on the vehicle dimensions, the overall length, it's 4.8 meters. The width is 1.9 meters. The overall height is 1.7 meters. The wheelbase is 2.9 meters. We have targeted a weight of 600 kilograms. So in terms of the battery capacity, when it's 100 kilowatts, it can go up to 450 to 500 kilometers. And when it's on 20 kilowatts, it can go up to 600 and 700 kilometers. So in terms of the suspension, I hope you can see the design down here of the charging socket, electrical engine, and the battery pack. Yeah, I think that's the end of my presentation. Thank you. Thank you.
Okay. Apologies. Thank you so much for this opportunity to present. Maybe Brandil, if you could mute, please. Okay, thank you. So first of all, thank you so much to the guys at AfriBot and GFT for this opportunity, for this hackathon, in order to present our ideas on what the future should look like. One thing that personally for me, I've always admired about these ultra-modern vehicles and these smart mobility vehicles is their design. It's the manner in which it's able to attract its target customers, its target passengers, and also its efficiency. So my presentation today is on Hyperion Model 1, a car which seeks to amplify those qualities. So let me just share my screen. Just give me a minute. Just give me a minute. So today we are going to learn about the Hyperion Model 1 vehicle, a smart urban mobility vehicle of the future. It can be agreed that in today's modes of transportation, one thing that is urgently needed is sustainability. We are in urgent need of sustainable transportation systems. We need systems which are efficient. We also need systems which are aesthetically beautiful and which have a sense of aesthetic value. And we also need systems which are comfortable to the passengers themselves. It's not all about efficiency. They also have to have that appeal to the passenger. How comfortable are they on that given seat? So today I'm going to take you through the Hyperion model that is designed to achieve that. So today we are going to talk about the mission for this model. We are going to look at the features and functionalities. We're also going to identify the opportunities, and I'm going to also lay out the future path for this system. So let's go. So the main purpose of actually coming up with this design or being able to participate in this competition is so that I can be able to contribute and to be at the forefront of the urban mobility revolution by being able to satisfy the constant need for efficiency, energy sustainability, comfortability, and aesthetic value by incorporation of quality design, sustainable energy systems, and artificial intelligence into the transportation systems that are used by the public commuters in our day-to-day activities, all in an attempt to boost its efficiency. So my name is Eugene Gusmao. I'm a fourth-year mechanical and manufacturing engineering student with a passion to change the world through engineering and research. And I hope that you'll be able to appreciate the model that I have for you today. So this is the model that we have, although I'll be sharing a more realistic version on Fusion after I'm done with the presentation. So just bear with me. So this is the model that we have. So it's really important that we have a clear understanding of the features and functionalities of the said system. We have this model here. You can be able to see it and you can be able to look at it, and you can be able to sort of like guess and pinpoint what are the exact features behind it. But from me as a designer, I can't be able to actually tell you what the system has in store for us. What is this model about? So that is what we are going to learn today. And as we begin delving into the features and functionalities of the proposed vehicle, it's important to note one thing about this vehicle. You realize that in our attempt to promote the whole aspect of sustainability, the concept of AI and the concept of automation is something that must come into play. We must be able to develop vehicle systems that can be in line with this so that they can be able to make day-to-day transportation from one given place simpler and easier. So to aid in that, the vehicle is fitted with the following control systems. We have the energy control system that is able to assist in energy management and take note of the various energy sources that are powering the system. Same applies to the power control system, which directly looks at the various power systems that we have been able to fit into our vehicle so that it can be able to power the vehicle and ensure its efficiency no matter the condition. We also have the vehicle body control system. This is the system that will be able to control the opening and closing of the doors and general mechanical functionalities of the vehicle that may be needed, even unloading and loading of luggages that the passenger might use. And we also have the lighting control system that will enable seamless and easy lighting during both the day and the night. So we'll start first by looking at the vehicle body. In the whole concept of design of this mobility system, of this mobility vehicle system that we have, one key area that is important to look at is the vehicle body. Does the body itself apply to the whole aspect of sustainability? Will it be able to support the vehicle in its running, or will it be the enemy in regards to how the vehicle is able to perform its day-to-day activities? So in the Hyperion Model 1, it is definitely not the enemy, and we are going to look at why. So number one, we are going to assess the aerodynamic shape. You do realize that for most vehicles and for most vehicle designers, the constant enemy that they are most probably trying to fight, even in the process of design, is air resistance and drag. And you find that that attributes even to the shape that most vehicles have on the road. they have that aerodynamic shape so that they can be able to reduce on this air resistance, so that it can be able to, and it can enable the vehicle to function efficiently. So we are going to look at the benefits of the aerodynamic shape that has been applied into the vehicle body, as you've been able to see. So number one is enhanced performance. Obviously, you do realize that with reduced drag, that will definitely mean that the vehicle will be able to accelerate more quickly, and it will be able to maintain high speeds with less effort. Number two is also the stylish design. You do realize that with aerodynamic shapes, as you've been able to identify with most vehicles that we have, they are able to give that sleek and modern that modern design that is generally appealing to the consumers. You know, we want a vehicle that is efficient, a vehicle that contributes towards a reduction of emissions, but we also want a vehicle that can sell. So definitely its aerodynamic shape is something that will be able to attract users towards this system, and will be able to enhance the vehicle's marketability and brand image, something that users, something that passengers, something that commuters can be able to relate to. Number three, the noise reduction. You do realize that an aerodynamic shape, that an aerodynamic design is capable of minimizing noise, is capable of minimizing wind noise, thus contributing to a quieter cabin and a more comfortable driving experience. Lastly, is on the improved stability and handling. You realize that with that aerodynamic shape, reduction of the air resistance that the aerodynamic shape provides as an advantage is something that can be able to effectively help manage airflow around the vehicle, reducing turbulence and lift. And you do realize that the effect of such is better stability at higher speeds and improved handling. You realize that the vehicle, you realize that the ride will now become more smoother and safer in urban environments. Something that we all definitely can be able to appreciate. And even for the HVAC systems in the vehicle, you do realize that there is some energy that is saved, since you do realize that the aerodynamic shape that we've been able to incorporate into our system can be able to heavily reduce the amount of work that the HVAC system has to do, to such an extent that a streamlined vehicle.
1 minute left.
Okay.
Yeah.
So let's look at another functionality of the vehicle body, that is its lightweight material. You do realize that incorporating this lightweight material promotes the aspect of strength and reduced weight, enhancing its performance and reducing on the wear and tear, also lowering on its production cost, since you realize that materials using less materials but stronger materials also reduces on the manufacturing costs. On the lighting system, as I've said before, is something that will be making use of the control system in order to control how it is able to light the vehicle during both daytime and during both nighttime. It will be making use of photoresistive sensors, providing all-round coverage of the body, as you've been able to identify on the body itself. So for the vehicle power system, yes.
Yeah, your time is up.
Excuse, I thought it was a maximum of 10 minutes.
Yeah. You just completed your 10 minutes.
Okay, just a request. Can I be added 1 more minute to finish up so that I can be able to show you the realistic version of the system, if that's okay?
You can send more information to the email that has been provided.
Okay.
So yeah, we are trying to chase time, so you can just leave it at that. Okay. The next group can present.
Excuse me, can I proceed? Okay, thank you. Thank you so much. What was I? Okay. Mhm. Okay. Okay. Okay, thank you.
Okay, I will go next. I hope you can hear me. I open up my software. Hope you'll be able to see my screen. Can someone confirm to me that you're seeing my screen? Oh, okay. My file is very big, so it's updating. So our car is called a silly car. It's a 4-seater car, and we designed the car using SolidWorks and Fusion 360. The Fusion 360 files, I don't know why it's taking too much time. I'll have to, let me close. Can someone else present? Like, I think my computer's crashed. I'll present next. Oh, man. Let me make Okay, can you see my screen? Okay, let me go to. So, I think let me open the more recent one. This one was for rendering in Visualize. It was a 2022 version. So I had to convert it into a 22, all the parts into 2022 version so that I could render it in SolidWorks Visualize. So this is the car, and we can see the interior. We also have so we have the LiDAR at the top, which is using light waves for to help in the semi-autonomous feature. We also have a long-range radar at the front. We have 3 cameras at the dashboard. Let me not rebuild. So we have 3 cameras at the dashboard, and then so I think when I'm sharing my screen, the computer crashes probably. Yeah, so as I was saying, we were doing the design in SolidWorks and Fusion 360. The top parts I designed in SolidWorks, and the rest were designed in Fusion 360. And then I was sent I was sent their final assembly. I think I have opened up the one for analyzing the CFD. So let me just load the results. So we did CFD on the shape. So I designed it as a surface, the top part. So I had to turn it into a body part so that I could perform CFD analysis. I think SolidWorks doesn't recognize surfaces. They are like 0 thickness. They are undertaken as 0 thickness. So if you look at the cut plot, this is the velocity in the Z direction at the cut plot at the right plane. You can see at the top part, the velocity is very low, and then if we look at the cut plot here, you can see that there is less pressure, and there's more pressure here. There's less pressure over here because this surface acts as an airfoil. And then you can also see the effect the spoiler has on the velocity at that side. So you can see the flow trajectories. If you look at it from the top part, I mean, both sides are symmetrical, so you will see more velocity on this side because it's more curved here. At the front, it's less, it has less surface area. And then if we look at the, let me look at this second one. This is the drag coefficient. The average is about -6. Let me if I can edit it. Yeah, so the question, this was the question, I put an equation goal to give me the drag coefficient of the car, which was, it's a negative because I used, the velocities in the negative Z direction. So I should have used, and I should have multiplied by -1, but the average drag coefficient is 0.6. And if you look at most cars, I don't know if I have that picture. If you look at cars, the body looks more like a van body, so it's somewhere there. And the Tesla, I think, is the one with the lowest drag coefficient. And then the next one is the SUV. So electric cars also need to also look at the drag coefficient. And so I don't know if Brian Kipkuri can present. He's my teammate. I'll share the screen. Brian Kipkuri, are you ready?
Thank you. So, I'm going to be pretty brief on my part. So, I was using the same model design. We'll share the designs document with the email. So, I'm going to talk about the electric powertrain, specifically what drives the car. And there are two hub motors on the front wheels, and each rated is 12 kilowatt. 12 kilowatt, yes, and top speed is 120 kilometers per hour, and they use far drive controllers, two far drive controllers rated around 800 amps at continuous current discharge. And in terms of battery capacity, it's a 35 kilowatt hour battery with an estimated approximate range of 200 to 250 kilometers on a single charge. So our basic design was just keep matters simple, create a 4-seater minus a driver, which is 3-seater, car, which is small, fuel efficient, safe. So in terms of charging, it can handle up to 52 kilowatt fast charging thanks to the lithium ion phosphate cells we used, basically from CATL manufacturer. We use prismatic cells at this point, and the onboard charger can support up to 10 kilowatt of charging. That's the level 2, and it uses a CCS2 type 2 charger port. Also, it has a solar panel roof with a capacity of 375 watts and added range of around 20 to 30 kilometers. And in terms of safety, it has adaptive cruise control and keeping assist and autonomous parking. That's all. I don't want to keep use much time on our side. And yeah, thank you for the chance to present.
How much time do we have left? Is it done?
Yeah, you have 3 minutes left. You can
Okay,
proceed.
let me just share this is the surface body which I was designing. We also have, these are the dimensions which I used to estimate it at the first time. And so it was more of trial and error until I got it. So all these surfaces, there are more and more surfaces. I mean, I layered them because you can't really edit SolidWorks is not really very good for surfacing. And you also can look at the zebra stripes. This gave me such a big problem. You can see there's discontinuity over here. Yeah. So this was the surface, and then what I did, I drew the whole surface, and then I split it, and then I form another body. So I don't know if I have like this is a split 1. Okay, split 6. This was actually the door. So I split it and I converted it into a part. Then I split it again, and I was able to make the 2 doors. I don't know if you can see. This was the render of the car. This is how the interior looks. This is the dashboard, the seats. Yeah, those are the lights. And yeah, I think I'll try to keep time. I think that's all.
Hello. Hello. Okay. Hi. Okay. So I'm going to share my screen. Okay. Sorry. Let me get to presenting. So I'm going to share my screen and so basically I decided to go into and start presenting for the small urban mobility car, and under that there's multiple components of the car that I had to make, for example, like the tires and all. And my car idea was basically a modern looking car designed for 2 to 4 passengers with a hydrogen fuel cell chassis, uh, because I felt that hydrogen fuel cells would be better to use than just normal electric components, because hydrogen fuel cells are more, I'd say, more renewable and also more easier to uh, do and maintain. And there's potential new tire designs that make use of renewable resources, such as the one that Michelin is using, which is made of things like orange zest, or things like paper or hay or metal, instead of non-renewable resources such as petroleum. And the car interior is just made to be like just a basic, simple car design of a modern car. So my inspiration was just all this, and now how I advanced as I did the model. Like, I hadn't completed it, but this is how it's going so far. So this is what I had started with, and this is how it's looking like as it progresses. So as you can see, it's just a sleek electric vehicle that just looks quite aerodynamic, though it's still in progress. And this was just in continuation of it. So this is how it's been looking like. And now the chassis of the model would look something of this sort. And like, as we're moving on in the world, electric vehicles are the more efficient way to go on and continue with life, because electric vehicles are very adaptable to serve various purposes, just instead of just beyond public transportation, as well as having performance and technology. For example, since urban mobility has to transport people all around constantly, if it was using things like petroleum or diesel, that would be very bad for the environment. So electric or hydrogen fuel cell powered vehicles are well suited for these environments. And also the charging would just be easily accessible with the charging station, the fast charging and the small charging. So, and also electric vehicles can integrate the safety technologies such as collision avoidance and things like sensors at the front and the back, cruise control and structural integrity from modern materials, and also reduces the risk of car-related accidents, for example, fuel leaks or things that may cause the car to stop working if it is using like the alternatives for non-renewable systems. And it's just very versatile as it can be, has multiple purposes as I mentioned. Yeah.
Thank you, sir. Okay, we are Team Mara. Okay, I'll switch off one of my screen for a moment. So we are Team Mara. We are three people. I am Warren Munene. We have Hilary who will present after me, and then there is Hilary who wasn't able to make the meeting. So we chose the name Imara because we are choosing to provide a solution that is for the long term. And as you know, Imara means strong, unshakable relatively. So let me share my screen. So that's the. Is my screen visible from your end? Okay. So this is our design. We are designing a modern PSV vehicle for the urban environment. So it's a 47-seater vehicle with details will be expounded with by Hilary. So I chose this design philosophy because it kind of looks old school, and so combining old school vehicles with tech sounds like a new idea, but technically not new. So yeah, that's basically it. So for the manufacturing, we haven't been able to properly design how the vehicle will be manufactured, but also the way the vehicle is designed is with reference to vehicles that are in the market within our Kenyan ecosystem. So the manufacturing process won't differ as much. No much research is needed into developing these for the market, basically in terms of manufacturing. So yeah, I think Amani, you can take over.
Okay, thank you. My name is Amani from Timimara. I'll present my screen. So for the interior, we are going with this design. So this is the bus, and then for the interior design, we have taken this, which includes an area here for people with disabilities. So these seats are actually foldable. They're mounted to the wall. They can be folded up, and there's a ramp here, as you have seen in Warren's presentation, where a wheelchair can come in and it sits in this place. The rest of the seats, which are in black, they are not retractable. They are normal seats. This is a big bus which can be used for urban mobility, given that we have a large population. For the seat designs, we have revolutionized to a very simple seat design, which include this metallic support which can be fabricated locally. And then for the upper part of the seat, it's a very easy seat to manufacture. The outer part is made of hard plastic with this curve here at the back, which gives it a spring effect so that it can handle shock absorption. The inner part is made of very soft cushioning material, and then the upper part is made of fabric. This is a very simple seat design which saves on weight, given that you are designing for that kind of mobility. And so this is the seat design, and then this is the seat arrangement, as you have seen. So this bus also combines other abilities, as it has been shown in the. So this is the render before we actually rendered it into a more stylish design. It has other abilities such as an extra battery pack being added here, depending on the capacity and the range we want. So the original range can be extended by adding another battery here at the back. So basically that's the interior design. I'll hand it over back to Warren to finish up. Thank you.
Thank you, Amani. So I believe that sums it up, and that sums it up. So thank you for the opportunity of robotics for enabling us to juggle with our creativity. Thank you.
Thank you, Engineer Justin. Thank you all for your presentations. I have seen your ideas. I've seen some great ideas here. What I think about the presentations and our expectations. We expected to have a design that we can take to production, and I think in the part of urban mobility, we expected a small size vehicle, and which some of you have presented. So for some of the presentations, like the first presentation, I feel like in the bodywork, what we most likely miss, I think I missed something like the side mirrors. I didn't see the side mirrors and the door knobs or such. even the charging port, I never saw it, something like that. So we are looking to see a design where the car itself has all the aspects of a vehicle. Yeah, you see things like the side mirrors I was talking about, the lights. Yeah, you see, we even since we are going to do the electric, we also need to include all the aspects of a car. Remember, we're using the car on the same roads we normally use to. Yeah, so you need to consider such aspects. Yeah, so I'll say those are my remarks. So I'll allow Engineer Brian to give also his remarks. Thank you.
Okay, Brian, I think Pius has summarized it all, but all I can say is that I've seen very impressive presentations. Some of the projects that have been presented are very detailed. That is something to note. So keep it up, guys. We'll just go through the designs and presentations and give you feedback by the end of the week. So thank you.
Hello. The hackathon has been a really good experience. I think we've learned a lot and been able to use features that maybe we never used before. And so I also had a question for submission. When is the deadline? Is it today night or when? From when are you starting judging so that we don't?
No, I just wanted to give sort of a vote of thanks for the hackathon itself. I think I have learned a lot in designing both the EV in both stages that I was looking at. As I said before, my interest is in a lot of robotics and being able to use the research that I did has also helped me a lot in that field. And I think it's great that you're trying to have a Kenyan company, a Kenyan made sort of car and EV at that. And yeah, I think it's a good way to sort of drive progress in Kenya in that sort of respect. So again, I just wanted to say thank you for the opportunity.
Thank you so much for this opportunity. I've been challenged. I've pushed my curiosity to the limits, and I can't wait for the next level to continue with this journey and just create something amazing from Africa. Thank you.